Another approach to using dummy variables, which has absolutely nothing to do with non-normality at all, is to allow for seasonality in financial markets. So if we estimate time series regressions and we use quarterly or monthly or daily or even half-hourly data on some financial or economic variables, then often the series that we're trying to explain why have patterns in them. In the context of financial markets, seasonal patterns have been very widely observed. Often these are called calendar anomalies in finance. So, for example, it's often been found to be the case that some financial variables systematically take on different values for some seasons than they do for others. For example, there's often been found to be day of the week effects in stock returns and stock return volatilities. So, for example, it might be the case that stock returns are systematically higher on average on Fridays than they are any other day of the week. We often find these seasonal effects or calendar anomalies, whatever frequency of data we use. Sometimes, if we had very high frequency data, we find that different things happen at the open and at the close of the market compared to other times of the day. So, for example, we often find more financial market volatility during the first half hour of market opening than we do at any other time of the day. If we have monthly data, often we find that these monthly data similarly have seasonal patterns in them. For example, we've often observed January effects in stock returns, and that's a systematic tendency for stock returns to be higher in January than any other month of the year. Often when stock markets crash, they seem to have a tendency to do so more in October than they would do for any other month of the year. So we could define seasonality as being a statistically significantly different type of behaviour during one season compared with others. Now, it turns out that the existence of seasonalities in financial markets isn't necessarily inconsistent with the efficient markets hypothesis, and we'll come back to that point a bit later on. But in the meantime, how can we econometrically deal with seasonalities? How can we capture them and model them in our econometric regressions? Well, the answer is, in order to capture seasonality in financial markets, we usually use a dummy variables approach. So to make matters simple, let's suppose that we had a set of quarterly data on some variable that we were interested in modelling, and we're interested in examining whether there are seasonal patterns in that data, or we're interested in allowing for seasonal patterns in that data. The way that we would allow for this seasonality in quarterly data is to set up a number of dummy variables which acted according to the frequency of the data. So if we had quarterly data, we could imagine setting up 4 dummy variables, one for each quarter. So we could define a variable D1t, which took the value 1 for quarter 1 and 0 everywhere else. A dummy variable D2t, which takes the value 1 in quarter 2 and 0 everywhere else, and so on and so on. So if we were to look at these dummy variables and the values that they would take on for each observation, we can see that dummy 1 takes on the value 1 for quarter 1 in 1986, quarter 1 in 1987, quarter 1 in 1988, and so on. Dummy 2 takes the value 1 in quarter 2, 1986, quarter 2, 1987, and so on. And obviously the value of this quarter 2 dummy variable will be 0 for every other observation apart from the second quarter. If we were to add up the values of those 4 dummy variables, we'd find that the value of those 4 dummy variables added was always 1 during every time period. And that's obviously true by construction, because we've got 4 dummy variables and only one of them takes the value 1 during each period, and all of the others take the value 0 during that period. So the value of the sum of these dummy variables will always be 1. We therefore need to be careful when we use seasonal dummy variables to ensure that we don't include both all of the dummy variables in the regression model and an intercept term. So if, for example, we had quarterly data, what we would need to do is to either just use 3 of the quarterly dummy variables that we could construct and an intercept term in the regression model, or we could use all 4 dummy variables but have no intercept term in the regression model. And whichever of those 2 approaches we used, we'd end up with the same kind of model at the end and the same residual sum of squares. The problem if we included all of the dummy variables, so if we had quarterly data, we included all of the dummy variables for the quarterly dummies, and we included an intercept, would be one of perfect multicollinearity between the sum of the quarterly dummy variables and the column of 1s in the X matrix that represents the constant term. So, as I said, we need to be clear and be careful that either we use 1 less dummy variable than we have given the frequency of the data and a constant, or we use all of the dummy variables together but no constant. Just to give you another illustration, if we had daily data and we set up 5 daily dummy variables, we could either use 4 of the daily dummy variables, and it wouldn't matter which of the 4 out of the 5 we used, and a constant, or we'd use all 5 daily dummy variables but make sure there was no constant in the regression. How does the dummy variable work? Well, dummy variables, like the ones that I've just described, are sometimes known as intercept dummy variables because they work by changing the intercept estimate for the regression model for each of the seasons. So let's come back to my example where we have quarterly data, and let's suppose we include a constant in the regression model plus 3 quarterly dummy variables for quarter 1, quarter 2 and quarter 3. What will be the value of the intercept terms estimated for each of the quarters in the sample? Well, the answer is as follows. In the first quarter, the value of D1 will take a value of 1, and the value of D2 and D3 will both be 0, so gamma 2 times D2 and gamma 3 times D3 will disappear from the model in quarter 1. If the value of D1 is 1 for quarter 1, then the estimated value of the intercept for quarter 1 will be beta 1 hat plus gamma 1 hat. Similarly, in the second quarter, the value of D1 and D3 will be 0. So all that will be left is D2, which will take a value of 1. So in the second quarter, the estimated value of the intercept will be beta 1 hat plus gamma 2 hat. In the third quarter, both D1 and D2 will take values of 0, so gamma 1 D1 and gamma 2 D2 will disappear, and D3 will take a value of 1. So in the third quarter, the estimated intercept would be beta 1 hat plus gamma 3 hat. Finally, in the fourth quarter, all 3 dummy variables take a value of 0, so D1, D2 and D3 are all 0, therefore the estimated intercept for the fourth quarter would just be beta 1 hat. So we can see that for each of the 4 quarters we'll get a different estimated intercept term. So the dummy variable works by changing the intercept term for each of those quarters and allowing for the average value of y, holding all the explanatory variables constant, to take different values for each of the quarters. Obviously, this is an intercept dummy variable that changes the intercept values and leaves the values of the slope coefficients constant. So the values of beta 2, beta 3, beta 4 and so on, that is the parameters attached to the explanatory variables x2, x3, x4 and so on, will always be constant through the seasons. They won't change. We could, however, if we wanted to, have a different set of dummy variables which allowed the slopes to change over time. But before we look at slope dummy variables, I want to look at an example briefly that uses these simple intercept dummy variables to allow for seasonalities in the context of a particular financial problem. So a paper by Brooks and Persand examined evidence for day-of-the-week effects in 5 Southeast Asian stock market index returns. The markets were South Korea, Malaysia, the Philippines, Taiwan and Thailand. The data that they used was from 31st of December 1989 to the 19th of January 1996, encompassing a total of 1,581 observations. So we have a set of daily data and we're interested in examining whether the average returns on each of these days of the week are statistically significantly different from other days of the week. So we run a regression of the daily returns on 5 daily dummy variables, D1t through to D5t. And D1t would be a daily dummy variable taking the value 1 on Monday and 0 everywhere else. D2 would be a daily dummy variable taking the value 1 on Tuesday and 0 everywhere else, and so on and so on. Now, the interpretation of dummy variable parameter estimates in this context, that is the interpretation of gamma 1 hat through to gamma 5 hat, will be as follows. The interpretation of these parameter estimates will be that they equal the average return on the day of the week of the dummy variable which they're attached to. So, for example, gamma 1 hat will be the average return on Monday, gamma 2 hat will be the average return on Tuesday, and so on. The reason that they do that is that D1 is obviously setting a dummy variable that takes the value 1 for all the Monday observations. So the job of D1, if you like, is to gather together all of the Monday observations and, in a sense, put to one side all of the others. So gamma 1 hat becomes the estimated average return on Monday. So if we look at the extent to which there is evidence for daily seasonalities in the Southeast Asian stock index returns, we can see that there is some evidence for seasonalities indeed. So, for example, there appears to be a significant Monday effect in Thailand and Malaysia, and those are positive Monday effects. That means there's, everything else being equal, a systematic tendency for returns to be higher on average on Monday than they are on other days of the week. There appears to be a negative Tuesday effect in Malaysia, a negative Wednesday effect in Taiwan, a positive Thursday effect in Malaysia, but there doesn't appear to be any evidence at all for daily seasonalities in the South Korean or Philippines data. So we can see some interesting evidence for seasonalities in those data. Now, how can we explain the existence of such seasonalities, and is their existence inconsistent with the efficient markets hypothesis? Well, at first blush, it would seem to be the case that if we have significant evidence that returns are higher on some days of the week than others, then that does seem to be evidence against the efficient markets hypothesis. Because this would suggest, for example, in Malaysia, that we would buy stocks at the opening of the market on Monday and sell them at the end of the market on Monday and take a short position in Malaysia on Tuesday. And if we did that every week, on average, we'd expect to net a positive return. However, if we look at the values of these coefficients, the values of the coefficients, which are in percentage terms, because the original returns were in percentage terms, measures the average return on each day of the week. So the average daily return in the Malaysian market is 0.002% approximately. Clearly, if we were to adopt a trading rule which said buy at the start of opening market on Monday, sell and take a short position at the close of the market on Monday, and then have a neutral position, for example, for Wednesday, Thursday and Friday, if we did that every week, we'd be making lots and lots of trades. And every time we made those trades, we'd be incurring some transactions costs. And it's likely that the transactions costs would wipe out these gains that we see. So we could only say we got evidence against the efficient markets hypothesis if it seemed that we were able to generate trading profits after accounting for transactions costs. Secondly, there are other reasons why we can observe seasonalities that are statistically significant, but which don't necessarily mean that the markets are inefficient. Often, there are things about the way that the market is structured or about the way that the world behaves which cause these seasonalities, but which are completely consistent with market efficiency. For example, it's usually the case that most macroeconomic announcements in the UK are made on Thursdays. So that often causes a tendency for Thursday in financial markets in the UK to be a more volatile day of the week, if you like, than other days of the week. If there's more volatility in the market on a Thursday, we might, for example, expect returns to be higher on a Thursday to compensate investors for this extra risk that they face. Similarly, often these calendar anomalies or seasonal effects are caused by things like the end of a tax year. So, for example, we might find something interesting happening in financial markets every April in the UK as a result of the end of the tax year at the start of April, when investors want to realise losses at the end of one tax year in order to reduce their tax burden. And what they might do is sell assets at the end of a tax year to realise financial losses and then to buy them back again at the start of the next tax year. If the investors decided to do that, that might obviously cause some patterns in stock returns, but in a way that wouldn't be inconsistent with market efficiency. So coming back to the idea of using dummy variables, as I said, instead of using intercept dummy variables, we could also envisage using slope dummy variables. So for example, to make matters very easy, suppose that we've got a set of data over time where there are just 2 seasons in it. For example, suppose we got biannual, in other words, twice yearly data. Or suppose we got data on opening and close of markets. So for example, we might have an observation on the open of the market, then the close on that day, then the open on the next day, on the close on the next day, and so on and so on. And we might think that the relationship between series is different depending upon whether we've got the opening observation or the closing observation. We could define a new dummy variable called dt, which takes the value 1 for all open observations and the value 0 for observations corresponding to the market close. If we use those dummy variables in a way in the regression model that we multiply the dummy variable by the regressor, that is, we have dt multiplied by xt, then that would be an example of a slope dummy variable. The slope of the regression model for the opening observations, where the value of d is 1, would be beta hat plus gamma hat. The estimated value of the slope for the closing observations, where dt takes the value 0 on the other hand, would just be beta hat. So you can see that by using dummy variables multiplied by the regressors, we can change the estimated slopes in the regression model. By using the dummy variables in this way, because we haven't included any intercept dummy variables, only the slope will change and not the intercept. Obviously, if we got quarterly data, we could use 4 quarterly dummy variables. But once again, we'd need to ensure that we didn't incur perfect multicollinearity by including 4 quarterly dummy variables multiplied by xt and including the original xt as a regressor. We could either use 3 quarterly dummy variables multiplied by xt and the xt on its own as a regressor, or we could use all 4 quarterly dummy variables multiplied by xt and not use xt on its own as a regressor. Equally, we could envisage a situation where we use both intercept and slope dummy variables in the regression model together. And whether we wanted intercept or slope dummy variables would depend upon whether we thought the seasonality affected only the average value of y. Okay? If the seasonality only affected the average value of y, but left the slopes or the relationship between y and the explanatory variables constant, then we'd only use intercept dummy variables. If, on the other hand, we thought that the seasonality changed the relationship between y and the explanatory variables, but left the average value of y constant through the seasons, then we'd only use slope dummy variables. If, on the other hand, we thought that the seasonality caused both the intercept and the slope to change, that is, it caused both the average value of y and the relationship between y and the explanatory variables to change across the seasons, then obviously in that situation we'd use both intercept and slope dummy variables. So we can do whatever we like. We can use intercept dummy variables or slope dummy variables or both, and whether we want to use one of those or both of them will depend on our ideas about how the seasonality impacts on the regression model. If we now go back to our example from the Brooks and Poisson paper that I just described, One interesting thing that we could do is to examine whether these seasonalities in the returns can be explained by different levels of market riskiness on each day of the week. And the way that we do that is to take our regression model with the 5 daily dummy variables in it and add to it a return on the world market portfolio multiplied by the daily dummy variables. So we add 5 more variables to the regression model. Each of those variables incorporates the return on the world market multiplied by a dummy variable for a day of the week. If we find, when we estimate this model, that the seasonalities that we found in the returns before have now disappeared, that is, if our alpha I coefficients are no longer significant, we could say that allowing for different riskiness on each day of the week, according to a CAPM type specification, has in a sense accounted for all of the seasonalities in the data. If, on the other hand, we find that the alpha i's are still statistically significant in the model, where they were statistically significant before, we would conclude that the different riskiness on each day of the week was insufficient to explain why the average returns were different on each day of the week in the markets where we found some seasonality in the first place. So if we now look at the results, this is what we get. So we've got our Monday to Friday dummy variables as we did before, and we've got what we might call beta Monday, beta Tuesday, and so on. And these are the estimated betas in the CAPM sense for each day of the week. And we only include in this table series where there were some seasonalities to explain in the first place, i.e. Thailand, Malaysia, and Taiwan. For the other 2 countries, we didn't find any statistically significant evidence of seasonalities to explain. We find that if we look at these results, the dummy variables for the slopes, that is the dummy variables multiplied by the return on the world market portfolio, seem able to explain some of the seasonality. So the seasonality in Taiwan has disappeared once we allow for differing risk on each day of the week, but the seasonality for Thailand and Malaysia remains, although for Malaysia it's slightly reduced. The Thursday seasonality has become slightly lessened in its impact. So our overall conclusion from looking at this would be that allowing for different riskiness on each day of the week, according to a CAPM type model, can partially explain the seasonality that we observe in the returns, but not completely. Interestingly as well, if we look at the differences in the values of the beta parameter estimates for each day of the week, we find that the estimated betas for each day of the week are very considerably different from one another. For example, for Taiwan, the beta estimates vary from 0.3 for all of the Wednesday observations taken together up to just over 1 for all of the Friday observations taken together. And that in itself, I think, is quite an interesting result.